the devices you've just seen have one thing in common. They're controlled by miniature electronic networks so small their anatomy cannot be seen by the naked eye. I'm talking about a fantastic new generation of microelectronics, like this tiny chip. There was a time when philosophers argued the question of how many angels might fit on the head of a pin, defying the laws of physics and reason. Well, today, if we take the liberty of equating angels with transistors, we can make a case for the existence of a modern kind of miracle, like fitting 7,000 transistors on one insignificant chip. In fact, by the time you hear me say this, that number will seem too modest. That's quite an accomplishment, as you'll see. But you ask, who cares how many transistors can be squeezed into tiny places you can't see? How does that affect me? Well, let me assure you, it is one of the most significant ideas of our time. It will affect changes in what we do from day to day in ways we're only beginning to see and understand. Imagine being able to store the entire contents of an encyclopedia, the languages of all the people on Earth, to make 1,000 decisions, all in the blink of an eye. All that power exists in silicon crystal, this man-made ingot, whose basic ingredient is found in ordinary sand, next to oxygen, the most common ingredient on Earth. The secret of turning sand to silicon crystal, then to those incredible electronic miniatures called chips, is available to anyone today. All you need are the best engineering brains and people who are willing to risk tens of millions of dollars to finance this technology, then years of research and development effort to make it work. Much of the work is done in clean rooms like this. The atmosphere in there is more sterile than an operating chamber. When you consider the highly complex designs of these new circuits measured in thousands of inches, you can see why the tiniest speck of dust becomes a boulder blocking a narrow road. Silicon wafers go through a series of treatments, each of which changes them, building layer on layer of personality. A single wafer finally yields 100 chips, each a miniature complex of thousands of components and circuits. There's a curious paradox here. It gets increasingly difficult to make them, yet they are less expensive. The reason for this is the steady advance of new techniques for packing more and more components into the tiny bits of silicon. The name of this amazing shrinking game is solid-state technology, the art of the integrated microcircuit, incredibly efficient and reliable, yet operating at speeds moving toward the speed of light. How in the world did all this happen? Well, it happened in 1947. 3 Bell Laboratory scientists in a lab, something like this one, achieved a remarkable breakthrough. They were able to send a weak electronic pulse through this tiny metallic device. Admittedly, it looks rather crude, but it made the signal amplify and switch. Up to that moment, the big vacuum tubes in the old family radio had been doing the same thing without much change for many years. Yet, this scrap of metal, only a fraction of the size of a radio tube, consumed a minute amount of energy, gave off practically no heat, and reacted much faster. How did they accomplish this?
We looked to nature for the answer. When we understood what nature was doing, we could control it.
Because their device transferred electrical resistance, the inventors called it a transistor, a word that's come to mean what radio once meant, and something more. It was the foundation of a new technology, microelectronics. In the world of technology, there are occasional milestones that have special significance, not always apparent at first. When this happens, our lives begin to change. The transistor was a special milestone. It has changed our everyday way of living, just as electricity did, just as the automobile did, just as air travel shrank our world. Soon after its invention, Bell Laboratories made transistor technology available, which helped spur the phenomenal growth of the electronics industry. In 1951, the first transistors came off the production line in this Western electric plant. Just consider the complexity of what's happened since then. To fabricate the equivalent of a single wafer containing 100 chips, the way it was done in the early transistor days, would have taken an experienced worker 10 years, working 8 hours a day, 10 million parts to assemble, tens of millions of terminals and soldering joints. Pure fantasy. There would not be enough material, people, and factories in the entire world to satisfy our needs today. The fact is, modern chip technology conserves not only operating power and human resources, but precious raw materials as well. The microchips being made here today are a new breed, so complex they're sometimes called computers on a chip. More correctly, they're microprocessors, but they do behave like miniature computers, combining many digital circuits, packed with memory and logic functions, and they have the calculating power of a wall-to-wall computer of 20 years ago. The microprocessor is the brain of modern electronic systems and can be programmed to do the most complicated jobs. It will store information coming in, compute the quickest way to carry out instructions, and let you know when the job's done. Our world has gone digital. We turn on with a digit 1, turn off with a 0. An electronic pulse or no pulse, simple as that. The microprocessor reacts to commands that come in the form of electronic signals, moving and switching streams of pulses at blinding speeds, all with zeros and ones. There are 18,000 transistors in that chip design, locked and sealed in silicon, connected by pathways as intricate as a street map of a great city. What you're seeing is just a tiny detail of a chip, about the size of one of a fly's many eyes. There are thousands of locations where information can be stored. This one is enlarged some 10,000 times. But why such emphasis on miniaturization? Is smaller really more beautiful? Chip designers are thinking small and smaller still because they have to. If they want their chips to gain speed, they've got to shrink the distances between circuits. If they can do that, a faster, denser, more efficient chip results. We have to think smaller because we're stretching our range of information, our communications lines, to the limit. We're an insatiable race of Gullivers in a shrinking Lilliputian world of technology. It has been said that since the end of World War II, the amount of information generated by our society doubles every 7 years. A daily copy of the New York Times, for instance, has as much information as the educated individual of the 16th century absorbed in a whole lifetime. To live in the 21st century, therefore, we'll need vastly different tools and instruments. The kind we're beginning to discover in the strange, diminishing architecture of the microworld. Even the common telephone, which has been with us for 100 years now, is evolving into an ideal instrument for the electronic age, more and more like a computer terminal. These 2 buttons, in fact, are reserved for computer communication and other far-out uses that even my generation will live to see in our homes. Tied into the Bell System's electronic network, we have a powerful tool for exchanging information. And microprocessors being introduced into the network itself are increasing its capacity to move information. We're just beginning to feel the effects of the microelectronic revolution. For the really far-out applications to come, we have to wait for these students who've grown up with calculators and computers to become the engineers of the 1980s and 90s. The transistor explosion of the 50s broadcast 1,000 innovations that would have seemed pure science fiction to most people 50 years ago. And we can see the microprocessor chip becoming the transistor of our time. Well, then what's beyond? Scientists are looking into DNA, trying to get a deeper understanding of how living things transmit genetic traits. Nature stores and transmits information in ways that make our present technology seem primitive. Perhaps in that direction lies the next breakthrough. They looked to nature for the answer. When they understood what nature was doing, they could control it.